Thank you for having me at CLAR 2022. My name is Noah Paul, up from the Civil, Environmental, and Agricultural Robotics Lab at the Technion Israel Institute of Technology. I'll be presenting design of a minimalistic torque-actuated variable rolling slip leg for robust locomotion. So legs, like robots and animals, traverse uneven and complex terrain. Think like a mountain goat climbing on a nearly 90-degree cliffside, or Boston Dynamics Spot, monitoring factory floors, or agility robotics Cassie hiking through a forest. However, with this increase in versatility comes an increase in complexity in design as well as control. So think Cassie, it has about 20 degrees of freedom, it has about 14 actuators, and uses a complex series of feedback and gate control libraries. So this makes an amazing robot, but in our lab in SEER, we focus on something called minimalistic robotics, where we try to take back some of that design and control complexity and put it into the structure of the robot. We call this like embodied control. So in order to take a step forward, let's take a quick step back and just remind ourselves how a constant slip works. So in the spring-loaded inverted pendulum model, our robots are represented as a point mass with a massless springy leg, with a set leg angle, a starting velocity, a set position, and a set leg length and stiffness. The robot then moves through flight, hits stance, compresses, and springs into apex. So this is a planar model. It's conservative. It uses one actuator for one output, and it models running fairly well, except it's stable with only a few degrees of that initial leg angle. It has a small basin of attraction, making it sensitive to terrain perturbations. However, in nature, we see a higher level of control over all of these leg parameters. So let's take a quick step and look at variable slip, theoretical model. Variable slip is a theoretical model that imagines if we had complete control over all of those leg parameters, over leg stiffness, over leg length, and leg angle. This would give us a much more robust model, but it would be a lot more complicated with adding 3 actuators, basically one for the knee almost for changing leg length, another actuator for changing stiffness. We want to try to pull that back a little bit. So control-wise, we can pull that back a little bit by binding the leg stiffness and the leg length to the leg angle. And then we can also try to make this a little more accurate to reality by including damping. So now we have a still kind of complex model, 3 actuators, 3 outputs, and we have included damping. So let's see if we can make it even more simple by looking at our model variable rolling slip. So in variable rolling slip, we try to gain all the benefits that we got from variable slip, however, keep it pretty simple. So here we have a spiral shaped leg, and by controlling that leg angle, we control the leg stiffness and the leg length and also the leg position. Due to the leg shape, our input angle alpha controls the output angle theta, the leg angle theta. Moreover, during stance, we have to consider changing leg length, changing stiffness, and rolling, making for some pretty complex equation of motions, but it's worth it. And then moreover, to keep the control kind of simple, we leverage an open loop control scheme called swing leg retraction. So in swing leg retraction, we kind of ask, what's the optimal leg angle and when we hit the ground to maintain constant energy? We previously shown in our research in our lab that this leads to stability through jumping to the same height. We call this YREL, relative to the terrain, and maintaining constant velocity. Moreover, we also shown that this, well, normally controlled with a linear equation through a polynomial controller, we can gain a little bit more stability. So by controlling the optimal relative height, that YRL, and forward velocity, we can find an equation that gives you the optimal leg angle at touchdown given the time from apex. So all this previous work in our lab in VR slip shows robustness over a single jump with damping or multiple jumps without damping. However, with damping, our previous work had no way to add back in energy during stance. So that's our gap, because we want to continuously jump. So if you're thinking we only have one actuator, the easiest way to add back in energy during stance would be to add in torque, so that we can continuously jump over rough terrain. However, the question then becomes, is there a similarly simple way to control that torque? So our hypothesis is to control that torque the same way we controlled SLR, with an open loop polynomial equation determining the magnitude of the torque relative to the time from apex. And by simultaneously optimizing the SLR and torque equations to get you back to that same relative height and keep your forward velocity the same, we can maintain constant energy. For our optimization process, we also simplified that. Rather than trying to optimize the leg over many multiple jumps over randomly generated rough terrain, we instead optimize it over a single jump process, changing only the initial conditions. For instance, here we're changing the terrain level while keeping the forward velocity constant, and on other runs we would change other variables. Through this, we can come up with, over a single jump, over multiple single jumps, an optimal polynomial for the leg shape, the leg stiffness, the leg, the SLR, and the torque. And then we can confirm this over larger randomly generated terrains in simulation. So our optimization flow basically ends up going as follows. We take in our initial forward velocity, our initial height, and our target Y relative. We optimize the leg shape for stiffness and the SLR without damping. Since there isn't a great way to come up with the damping during like a simulation, we then take that and we either find it in FEA with our leg shape that we generate, or experimentally by 3D printing it and putting it in a universal testing machine. And then we take all those parameters that we found before and do our simultaneous optimization, and for constant forward velocity and YRL. In order to explore the effects of optimizing for YRL, we generated 3 different legs, each with a different hopping height, each with a Y initial equals YRL of 0.3, 0.35, 0.4, with an initial forward velocity of 0.8 meters per second, optimized for terrain variations of plus minus 0.05 meters. And then we took those legs and we pushed them past the optimized terrain variation, or rise, and ran them on terrain variations of plus minus 0.1, 0.2, 0.3, and 0.4. So for instance, here you see 3 legs running across terrain that they're optimized for, the 0.05 meters. And then we push them past 0.02, and we show that the only here 2 legs survive. And by the time we push it to 0.04, only 1 leg survives, the highest jumping leg. So in order to explore this further, we gave each leg the goal of 50 hops over 30 randomly generated terrains for each rise. And we found overall that there was the higher jumping leg had a higher degree of survivability. We suspect this is simply because a higher jumping leg has a higher clearance. So it's able to just clear any terrain that would be problematic for other legs. Then in a separate experiment, we wanted to show the efficacy of a spiral shaped leg over a straight leg. So we generated 2 legs, each with the same max length, each optimized with the same single jump process, each optimized with torque compensating for damping and SLR for stability, and then also for the same rise, the same plus minus 0.05. We set them on a random terrain, and we see that the straight leg deviates from the target Y relative, while the curved leg sort of holds on there. And the straight leg deviates pretty wildly, giving you a higher likelihood of crashing. So here we see those deviations from the target Y relative. And we can see from this that both the straight leg and the curved leg benefit from torque. They're both compensating, and they're both multi-jumping. However, the curved leg's variable geometry, the variable stiffness, variable leg length, adds stability through its ability to compensate for perturbations. All this is done with a single actuator, minimalistic design, open loop control, and single jump optimization process. Moving forward, we want to optimize this leg for different torque SLR profiles on the same leg shape for different terrains and speeds, allowing for user control over the target height and target speed while hopping. We want to also take this robot that you see here that's made for just doing SLR. It actually has a clutch that disengages during stance. There we go. And it just sort of rolls through and then hops back up. And we want to outfit it with a motor so it can do torque insertion during the stance and increase the running length of this boom. It's only able to do one jump here. So we can confirm our results on a real world model. I'd like to thank my advisor, Amir Degani, as well as Adar Gaathon, whose work this is based off of. And any questions?
Thank you very much. Perfect timing. Please, the question.
Thank you. Could you maybe specify what kind of contact integration schemes you're using and how you think these would influence your results?
What do you mean by contact integration schemes?
Do you assume soft contact, and how do you simulate when the contact switch happens?
It doesn't really need to, that's sort of the point of SLR, right? So SLR is sort of a timer running. As soon as you hit apex, as soon as you start falling, you start swinging your leg back, as if you're about to hit the ground always. And then once you hit the ground, you just start moving into, you roll through and then hop back up. You're saying to understand when to apply torque? Or, I'm not sure if I understand.
Maybe you can also take this.
Good chat after.
Yeah.
I'd love to.
Any other question? If not, just a short question to you.
Sure.
I think that terrain, as we see, is with low dissipation of the energy is very hard.
Yes, it's very hard.
That what do you think? Are you plan to test on the soft, because the behavior can look quite different?
I think it'd be really interesting since there's already like damping in the leg, but you'd have to probably do, I suspect you'd need to do another optimization considering the soft terrain. And you'd also then need some sort of way to know if the terrain that you're landing on is soft or hard. So you know what portion of the leg to land on.
Yes, because maybe you will be having not enough energy to jump.
Exactly.
Take off. Okay, I think we are short in time. Then thank you again for a very interesting presentation combining the simulation and the experiment.